we are going to be looking at Lesson 3, and the objectives for Lesson 3 are to simplify exponential expressions, and then we're also going to get some more definitions. We're going to define what a base is, what a power is, and what an exponent is. Now, what's y'all's recollection of what those three things are?
The base is like the number that the exponent's on?
The base is the number that the exponent is on, right? Okay. What does the exponent tell us?
How many times you multiply by itself?
How many times to multiply the number by itself? How many times the base is being multiplied by itself? What's a power then?
So when you raise it to the second power, it's like 3 times 3.
Yeah, I'm trying to.
Does that make sense? It's how many times you multiply it by itself.
That's the exponent, right?
But that's the, like.
I'm trying to. It's like the power of the exponent.
Okay. Let's talk about 16 as a power of 2.
Then you just do 16 times 16.
No, 16 as a power of 2.
Oh, yeah, 2 times 2 is like
2 times 2 times 2 times 2 is 16. So Charlie's got it right here. 2 to the 4th power is equal to 16. So if we're talking about an exponential statement, this is an exponential statement. Now, 16 is the what?
The
4th power of 2. Okay, so a power is the result of an exponential operation. Just like a product is a result of multiplication, a difference is a result of subtraction, a quotient is a result of division, a power is a result of an exponential operation. 16 is the 4th power of 2. It's 2 to the 4th. Okay, so this is a power expression. 2 is the base, right? 4 is the exponent, and 16 is the power. Okay, now this is 2 to the 4th is also, considered a power expression. It's a base with an exponent is a power of that number. Now, power is almost synonymous with exponent the way we use it. 2 to the 4th, we sometimes say that's 2 to the 4th what? We say that's 2 to the 4th power, right? The power is actually the result or the entire expression. Okay, so that's just to kind of clear that up. So those are some definitions we'll look at, and here's some more of these. You probably don't need to write these down. I think you probably already know these today. It's pretty much a review. An exponent can be used to show repeated multiplication. Now the key word here is can be. Okay, we'll talk about that in just a minute. Can anybody think of when an exponent wouldn't be used to show repeated multiplication? First power certainly doesn't show repetition. I agree with that. 0, yeah, that doesn't really show repeated multiplication, right? Anything to the 0 power is equal to what? 1. What about other powers? Negative powers? Have y'all dealt with negative powers?
Yes.
We have to cross the line and change the sign.
The negative powers flip things, right? Right? And remember, fractional exponents. Y'all remember fractional exponents? What about 16 to the 1/2 power?
No, we didn't do that.
Yeah, you did.
We did.
We did.
No, we didn't.
Miss Sorrells never taught us. Yeah, Miss Sorrells never taught us this.
Yeah, she did, because the 5th period was all over it. Y'all just didn't catch it. All right, 16 to the 1/2 power is equal to 4.
I sort of remember.
It's a square root, right? So fractional exponents indicate roots of things. Y'all pay attention. Listen up carefully. The fractional exponents represent roots of things. Okay? The 1/3 power, 8 to the 1/3 power is 2. That's the cube root of 8.
Oh, you
Okay.
just divide it by 3?
No, you're not dividing it by 3. You're taking the cube root. Now, that's not important. We'll have a lesson on that much later, but this says an exponent can be used to show repeated multiplication. That's really only true if the exponent is a natural number. Okay? Now, a natural number will show us repeated multiplication. And the textbook actually says if the exponent is a natural number, it is used to show repeated multiplication. Now, the base of a power is the number that's being used as a factor. Notice that says the base of a power. 16 is 2 to the fourth. 2 is the base, 16 is the power, 4 is the exponent. All right? Now, number used as a factor, the exponent is a natural number. You know, I've got an asterisk there that kind of goes back to what we just talked about. It can be, and this asterisk kind of relates to that. If it's a natural number, then it's showing us how many times the base is used as a factor. If it's a negative number, or if it is a fraction or irrational or rational number, it's telling us something else. Okay? Now, is everybody okay with that? All right, so let's look at some examples. Seven to the third power. What's the value of 7 to the third power?
It's 49 times 7.
So again, and let's just try to challenge ourselves like we did with the bell work to do this mentally. 343 comes from 49 times 7, right? What's 40 times 7? 280. 9 times 7 is 63, and 280 plus 63 is 343. Now you could write that out and multiply it, and on a test you absolutely should. Okay, but let's stretch our mental abilities. 7 to the third power is 343. So 343 is the third power of 7. Okay, all right. 0.3 to the fourth power. Be careful on this one. Don't answer quickly. But figure out what that would be. Where would you start?
3 times 2? Or 0.3 times 0.3?
Or really 3 times 3, right? We can deal with the decimals later. 3 times 3 is,
9.
and we need to do that twice, right? 3 times 3 times 3 times 3 is 81, right? 9 times 9 is 81. How many places behind the decimal? 4, right? Because it's 0.3, and so I got 0.0081. Yes? All right. Now, that's quicker to do mentally than it is to do by hand. You just have to know how to manipulate things. 3 to the fourth is 3 times 3 times 3 times 3, which is 9 times 9, which is 81. All right? That'll come up a lot in your life, your mathematical life anyway. 3 to the fourth is 81. You'll see it on the ACT and other places. And if you know it, you can do that problem more quickly. All right, next example. 1/2 to the fifth power.
Wouldn't it just be 1?
Well, what does it mean? Let's go strictly to the definition of things. 1/2 to the fifth power is 1/2 times 1/2 times 1/2 times 1/2, right? And if I'm doing that, then I'm multiplying 1 times itself.
It's like 2 to the 2.
It's 1 over 2 to the fifth, right? What's 2 to the fifth?
32.
Okay. 1 over 32. And we know that because 2 to the fifth is 32. And here's something that you should know, guys, and I want to kind of come over to the side here. You should know the powers of 2 up through 10. You really should. You should know those pretty readily. 2 to the 0 is 2 to the first is 2 to the second. You're just doubling it every time, right? 2 cubed is 2 to the fourth, 2 to the fifth. Sorry, that's kind of ratchet there. 2 to the sixth is 64. Double it again. Double that. 256. Double that, we get 512. And then 2 to the 10th is
1,024.
This is a, y'all listen, this is a magic number.
Why? Because it's,
Ooh. Somebody know?
I forgot.
What?
Karis has forgotten. I mean, Aspen.
I know it's a game.
I know,
No, it's
right?
not.
That's why I can't remember.
Okay. Now, at some point, this number is going to come up again. Y'all listen. Shh. Listen. At some point, this number is going to come up again. I'm going to make an assignment for you to kind of go out and do some research on 1024. What's the significance of 1024? But every single day of your life is impacted by that number, and you don't even know it. All right? So, but you need to be familiar with the powers of 2 up through 2 to the 10th. You need to be familiar with 3 up to 3 to the 4th. And we'll talk about those as they come up, because it's going to make you be able to do things more quickly. All right? Now, let's go to the next one. What is 10 to the 3rd power? 1,000. 10 to the 3rd is 1,000. So 1,000 is the 3rd power of 10. So 1,000 is the power, 10 is the base, 3 is the exponent. Okay? Now, simplifying expressions using the product property of exponents. Now we're switching from numbers here to expressions. Now, expressions can contain numbers, variables, or a combination of numbers and variables. So we're going to be dealing with some algebraic aspects of exponents here. What are the rules that govern algebraic operations? Yeah. See, this statement says the product of powers. What's a power? Something that has a base and an exponent. If the product of powers whose bases are the same can be found by writing each as a repeated multiplication. So we could take 5 to the 4th times 5 to the 5th, and we could write it as 5 times 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 5, which is 5 to the 9th, right? There's 9 5s there. So what's the rule that applies when you're multiplying powers? You add the exponents of the bases that are the same, right? So you add the exponents of like bases. And this is kind of, that's the rule. When you multiply, you add the exponents of like bases. This is one of those rare days of the year that I cover the same lesson with you guys, Algebra 1 students, and my college algebra students. We talked about this today. We did all 6 laws of exponents in one day, and we'll cover those over 6 separate lessons. But they've had it twice before they get to us. So.
Laws of exponents, like if you subtract, you do that, or if you...
Right, so what do you do with exponents when you're multiplying? What do you do with exponents when you're adding? What do you do with exponents when you divide? Those are the laws of exponents, right? And you guys you know these, but we'll perfect them and make the problems a little bit harder and more challenging. So here's the mathematical rule. If m and n are real numbers and x is not 0, then x to the m power times x to the n is equal to x to the m plus n. Now, what is that rule telling us? If you multiply, you add exponents, right? Isn't that what we're doing there? Now, I want to point out that this says if x and the m are real numbers. So what's the significance of that?
They have to be
Rational.
They could be rational or irrational. Okay? Now, this says if they're real numbers. I'm not sure right off the top of my head, but I would think that the rule for complex numbers would be pretty close to the same thing. But I'd have to do a little research there. Okay? But x to the m times x to the n is equal to x to the m plus n. What this rule is telling us is what the previous fact said. If you multiply, you add the exponents of like bases. So when you multiply things, you add the exponents of like bases. Let's look at a few examples. X to the 5th times x to the 7th times x squared. X to the 14th, because 5 plus 7 plus 2 is 14, so that would indeed be x to the 14th, right? Any questions there? All right. What about this one? Don't go too See, that's how, and I even warned you not to go too fast, right? So you got to only add the exponents of what?
11.
Like bases, right? So I'm going to add these 3, and then I'm going to add these 2, because those are the like bases. I have m's in this problem, and I have n's in this problem. So the result is going to be m to the 9th, n to the 13th. That's an instance where if you go too quickly trying to get that answer, trying to get that test finished, trying to get that quiz finished, you might make a mistake. Okay? Now, let's have a look at, is there another one here? There's not. Your homework from this lesson, and this is lesson 3. I need to write that up here. Lesson 3 homework. And a lot of times I try to put the page numbers up there. But you go to the end of lesson 3. Go to the end of lesson 3 and you'll find this assignment. Now, I want to explain that in just a second. I want you to do the practice problems A through G. Now 1 through 15 is all, and then just the odds on these. Okay, any questions? Y'all understand that? The homework squares are uploaded online, and you can do that. Okay, be sure to like, comment, and subscribe.